In the vast emptiness of space, countless mysteries remain unsolved. And every ray of light that reaches us is a message from the distant past. Today, we embark on a journey through frozen giants and dying worlds, across ancient belts and forgotten moons. And then, beyond the boundaries of time, we'll pierce through interstellar space, glide past ancient suns and fading red dwarfs, witness the birthplaces of stars, flashes of life in the heart of darkness. Awaiting us are galaxies veiled in shadow, supermassive enigmas, currents of dark matter, and gravitational echoes of worlds long gone. This is more than a journey through space. It is a descent into the soul of the universe, from the first whisper of the Big Bang to the furthest edges of time itself. Get ready. We begin now. Of all the countless wonders scattered throughout our vast solar system, there are certain places shrouded in a veil of mystery, captivating us precisely because they are so distant and alien. Among these enigmatic worlds, two planets stand out, icy giants hidden at the cold, dim fringes of our solar system. Their bluish hues, turbulent atmospheres, and secretive inner worlds continue to challenge our imagination, inspiring curiosity and exploration. Of course, we are speaking about Uranus and Neptune, the solar system's distant sentinels. It may seem astonishing that these giant worlds were discovered relatively recently. Jupiter and Saturn have been known since ancient times, visible to the naked eye as wandering stars in the night sky, intriguing humanity for millennia. But Uranus was first spotted only in 1781 by the brilliant astronomer William Herschel. Using what by today's standards was a fairly modest telescope, he saw what he initially mistook for a comet. However, careful calculations revealed this object to be orbiting the Sun at a distance far beyond Saturn, making it the first new planet to be discovered in recorded human history. The discovery of Uranus opened a new chapter in astronomy, expanding our cosmic horizons. Yet the discoveries didn't end there. Observations of Uranus's orbit soon revealed unexplained perturbations, as if something even more distant were pulling at it, affecting its path around the Sun. Based on precise mathematical predictions by astronomers Urbain Le Verrier and John Couch Adams, Neptune, an even more distant giant, was discovered in 1846. This marked one of the greatest triumphs in the history of astronomy, a planet found not simply through observation, but through mathematics alone. Both Uranus and Neptune reside in a region far from the warmth of the Sun, at distances of 19.2 and 30 astronomical units respectively. This means sunlight reaching these planets is hundreds of times weaker than on Earth, making their worlds unimaginably cold and dark. Uranus, slightly closer, completes one orbit around the Sun roughly every 84 Earth years, whereas Neptune, further out, takes an astounding 165 years to circle the Sun just once. Despite such differences in orbit, both planets share remarkable similarities, enough so that scientists categorize them as ice giants. The term ice giant highlights their unique composition compared to the gas giants Jupiter and Saturn. Unlike their larger gas siblings, whose thick atmospheres consist primarily of hydrogen and helium, the inner layers of Uranus and Neptune are rich in heavier substances, ices of water, methane, ammonia, and possibly heavier elements. In fact, even though we call them ice giants, deep within their interiors, pressures and temperatures rise so dramatically that water and ammonia behave in ways unimaginable on Earth, forming hot supersonic oceans with temperatures exceeding several thousand degrees Celsius. According to scientists, beneath their dense atmospheres lie extensive layers composed mainly of these exotic, electrically conductive fluids surrounding rocky Earth-sized cores. The atmospheres of Uranus and Neptune primarily consist of hydrogen and helium, but unlike the gas giants Jupiter and Saturn, their vibrant blue colors come from significant quantities of methane. Methane in their upper atmospheres absorbs red wavelengths of sunlight, reflecting primarily blue-green shades back into space, giving these distant worlds their strikingly beautiful aquamarine appearance. However, despite their apparent tranquility from afar, their atmospheres are anything but calm. Uranus and Neptune both experience powerful storms, raging winds, and chaotic turbulence, far surpassing anything found on Earth. On Neptune, wind speeds have been measured reaching nearly 2,000 kilometers per hour, more than twice the speed of sound, making them the fastest planetary winds ever recorded in the solar system. It's precisely these contrasts between serene visual appearance and violent climatic phenomena that intrigue astronomers. Interestingly, Uranus presents another peculiar trait that sets it apart from all other planets. It rotates on its side. While most planets have axes slightly tilted, like Earth's moderate 23 degrees, Uranus is tipped over by almost 98 degrees, essentially lying sideways relative to its orbit. Scientists believe a massive collision with another celestial body billions of years ago is responsible for this peculiar orientation, literally knocking the planet off balance. As a result, Uranus experiences extreme seasons. Each pole faces the sun continuously for 21 Earth years at a time, plunging the other hemisphere into a long, freezing darkness. This unusual arrangement leads to prolonged periods of summer and winter, unlike anything experienced on Earth, each lasting decades. Neptune, though more conventionally oriented, also surprises scientists with its fierce atmospheric conditions. Winds on Neptune can reach speeds of up to 2,100 kilometers per hour, making them the fastest recorded in the solar system, roughly 3 times faster than Earth's most violent hurricanes. One of Neptune's most striking features, observed by the Voyager 2 spacecraft in 1989, was the so-called Great Dark Spot, a storm larger than Earth itself. Intriguingly, when the Hubble Space Telescope attempted to observe this storm a few years later, it had mysteriously disappeared, indicating how rapidly weather conditions change in Neptune's turbulent skies. Unlike Earth's hurricanes, fueled by solar heat, Neptune's storms draw their energy from the planet's internal heat source, radiating outwards into the freezing cold vacuum of space. Despite their fascinating atmospheres, both planets also boast intricate ring systems, though far less spectacular and visible compared to Saturn's famed rings. Uranus has 13 known rings, dark and narrow, consisting of particles likely composed of ice mixed with carbon-rich dust, giving them a dark charcoal gray color. Neptune's rings are equally mysterious. They were definitively confirmed only by the Voyager 2 spacecraft flyby in 1989, composed primarily of dust and ice particles, dark, tenuous, and elusive. These rings remain a fascinating mystery for astronomers, hinting at a violent past filled with cosmic collisions and fragmentation events. In addition to rings, both Uranus and Neptune possess numerous moons. Uranus has 27 known satellites, most notably Titania, Oberon, Miranda, Umbriel, and Ariel, each a unique, icy world with a complex geological history of its own. Neptune's moon system, though less numerous, counts among its members Triton, one of the most geologically active moons in the entire solar system. Triton boasts geysers erupting from its frozen surface, ejecting icy particles several kilometers high into its tenuous atmosphere. Scientists suspect that beneath Triton's icy crust, there may exist a subterranean ocean warmed by tidal heating, similar to moons like Europa and Enceladus, raising intriguing possibilities for extraterrestrial microbial life. Since their initial discoveries, Uranus and Neptune have been visited only briefly by a single space probe, Voyager 2, which flew by Uranus in 1986 and Neptune in 1989, sending back the first detailed images and vital data on atmospheric conditions, magnetic fields, rings, and moons. Today, no dedicated missions to these distant worlds have yet been undertaken. However, astronomers worldwide increasingly advocate for ambitious future explorations. Concepts for orbiters and atmospheric probes have been proposed, aiming to unravel the enigmatic ice giants' countless mysteries. From their bizarre magnetic fields, which are inexplicably offset from their rotational axes, to their hidden interior oceans and peculiar chemistry. Studying Uranus and Neptune goes far beyond mere scientific curiosity. These distant worlds hold critical clues about the early formation and evolution of planetary systems. Understanding their composition, history, and formation can shed vital light on the distribution and diversity of exoplanets throughout our galaxy. Moreover, their role in sculpting the outer solar system and possibly influencing life's emergence on Earth is still not fully understood. Every bit of knowledge gleaned from these remote worlds opens doors to comprehending planetary evolution, habitability conditions, and the intricate dynamics shaping our universe. Thus, when we gaze towards Uranus and Neptune, we are reminded of how mysterious and unexplored even our close cosmic neighborhood remains. Each new observation and future mission promises thrilling discoveries, perhaps even rewriting our fundamental understanding of planet formation and evolution. Who knows, perhaps beneath the icy clouds, we might discover secrets that could rewrite our understanding of what constitutes conditions favorable for life. The ice giants hold profound implications not only for planetary science, but also for the eternal human quest to understand our origins and place in the cosmos. With every future mission, we come closer to decoding the stories locked within these distant, silent worlds, waiting patiently at the solar system's edge. For decades, Pluto remained one of the most enigmatic objects on the outer fringes of the solar system. Even after its discovery, when astronomers could barely make out its faint glow against the backdrop of stars, it remained overshadowed by the much larger and more massive giant planets. Only in the late 20th and early 21st centuries, thanks to technological advancements and the growing interest in dwarf worlds, did Pluto step into the limelight. Many of us still remember the controversy surrounding its status. For a long time, it was considered the ninth planet, but in 2006, the International Astronomical Union revised the classification, relegating Pluto to the category of dwarf planets. Despite this formal demotion, this distant world on the edge of the solar system continues to attract the interest of scientists and space enthusiasts. Its icy plains, breathtaking mountains, and thin, ever-changing atmosphere depict an extraordinary world where temperatures drop to exotic extremes and sunlight barely illuminates its desolate landscapes. Today, we embark on a journey through Pluto, reflecting on its history, characteristics, exploration, and why it remains crucial for understanding the evolution of the farthest reaches of the solar system. From a historical perspective, Pluto was discovered relatively late in 1930, thanks to the observations of American astronomer Clyde Tombaugh at Lowell Observatory. At the time, astronomers were searching for Planet X, a hypothesized object believed to influence the orbits of Neptune and Uranus. Although modern understanding of planetary dynamics suggests that Percival Lowell's and others' calculations contained errors, this search program ultimately led to Pluto's discovery. Back then, its planetary status was unquestioned, as no comparable trans-Neptunian objects had yet been found. Over time, as astronomers discovered other bodies in the Kuiper Belt, such as Makemake, Haumea, and later Eris, the question arose, should Pluto still be considered the unique ninth planet, or was it merely one of many icy objects beyond Neptune? In 2006, the IAU introduced a new definition of planet, which Pluto failed to meet, primarily because it had not cleared its orbit. Thus, the category of dwarf planets was established. However, despite this reclassification, Pluto's significance in astronomy did not diminish. On the contrary, the debate over its status fueled further interest, and the New Horizons mission, which we will discuss later, became one of the most impressive expeditions to the outer solar system. In terms of basic characteristics, Pluto is relatively compact. Its diameter is approximately 2,377 kilometers, making it smaller than the Moon, which has a diameter of about 3,474 kilometers. Pluto's mass is around 1.3 times 10 to the 22nd kilograms, which is about 6 times less than the Moon's mass. Its estimated density ranges from 1.85 to 2.0 grams per cubic centimeter, indicating a substantial proportion of rocky material in addition to ice. For comparison, the icy moons of Jupiter and Saturn often have lower densities. Thus, Pluto represents a unique hybrid. Its composition includes water ice, nitrogen, methane, and rocky material. In terms of size, Pluto is comparable to some of the largest moons. Io and Europa are slightly larger, but it closely resembles Neptune's moon Triton in both size and many geological features. This suggests that Pluto is a representative of the Kuiper Belt, an icy body that formed on the outskirts of the solar system, where low temperatures and volatile compounds dominated its early environment. Regarding its internal structure, scientists believe Pluto has a relatively large rocky core, surrounded by layers of water ice and other frozen compounds. Estimates suggest that the core could make up 50 to 70% of Pluto's volume. At extremely low temperatures, below -200 degrees Celsius, ice behaves like rock, but under high pressure and slight warming, deeper ice layers may exist in a semi-molten state. Some models predict that beneath Pluto's crust, a subsurface ocean of water mixed with ammonia could exist, though confirming this hypothesis requires more detailed data. Nonetheless, signs of active geology, such as ice mountains, canyons, and possible cryovolcanoes, suggest that processes resembling those seen on the icy moons of giant planets may also occur on Pluto. Scientists speculate that radioactive decay in the rocky core might generate enough heat to sustain a partially liquid layer beneath the surface. This is particularly intriguing as it challenges the earlier assumption that such a small and distant body should be frozen in absolute stasis. A major breakthrough in Pluto exploration came with NASA's New Horizons mission, launched in January 2006. The probe traveled to Pluto for over 9 years, passing Jupiter and using its gravity for acceleration. By the summer of 2015, New Horizons reached Pluto's vicinity, performing a historic flyby on July 14, 2015. During this brief encounter, the spacecraft collected a wealth of data using its cameras and spectrometers, capturing Pluto and its moon cairn in stunning detail, revealing surface contrasts and providing new insights into its atmosphere. For the first time, humanity saw Pluto not as a tiny, blurry dot, but as a complex world featuring a vast nitrogen ice plain, unofficially named Sputnik Planitia, towering ice mountains, and even a hazy blue sky and scattered sunlight. These images and measurements exceeded expectations, showcasing a younger and more dynamic terrain than previously imagined. Examining Pluto's surface, the most striking feature is the bright, heart-shaped region known as Tombaugh Regio. The left side of this area, called Sputnik Planitia, is a massive plain of frozen nitrogen. This nitrogen ice, mixed with methane and carbon monoxide, appears to flow similarly to glaciers on Earth, smoothing out craters and irregularities. Observations indicate a lack of significant impact craters in this region, suggesting that the surface has been geologically active within the last tens or hundreds of millions of years. Another striking feature is the presence of mountain ranges several kilometers high, composed primarily of water ice, which behaves like solid rock under Pluto's extreme cold. Deep canyons and extensive dark regions near the equator appear to be older terrain covered in a thick crust of water ice and other materials. Although Pluto is, on average, about 5.9 billion kilometers from the Sun, more than 39 astronomical units, it possesses a thin but noticeable atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. Surface pressure is extremely low, only a few microbars, about 100,000 times less than Earth's. However, New Horizons detected a striking blue haze caused by complex hydrocarbons, tholins, forming in the upper atmosphere under ultraviolet sunlight. This atmospheric dust creates a delicate glow, and under certain lighting conditions, it forms blue bands around Pluto's disk. The atmosphere constantly escapes into space and partially freezes as Pluto moves farther from the Sun, sublimating again when the planet approaches perihelion. Some scientists compare this breathing process to seasonal changes on Earth, albeit on a much longer timescale, as Pluto's orbit around the Sun takes 248 years. Why is Pluto so important and unique despite losing its planetary status? First, it offers a window into the history of the Kuiper Belt, a region where temperatures remained extremely low for billions of years, preserving volatile compounds. Pluto and its siblings, such as Makemake, Haumea, and Eris, help scientists understand the early solar system's formation. Secondly, Pluto and its largest moon, Charon, with a diameter of about 1,212 kilometers, nearly half of Pluto's size, form a binary system with a center of mass located outside Pluto itself, an unprecedented case among former planets. Their tidal interactions may influence their internal activity. Lastly, Pluto's surprisingly young surface, ice mountains, and potential cryovolcanism suggest a more dynamic geological history than expected for such a small, distant body. The modern era of Pluto exploration is inseparably linked to the New Horizons space probe. Launched on January 19, 2006, from Cape Canaveral, the spacecraft reached Pluto's system in July 2015, performing a historic flyby at a distance of about 12,500 kilometers from the surface. During those brief hours of its closest approach, the probe collected an enormous amount of data, transmitting it back to Earth over the following months and even years, due to the extremely slow transmission speed caused by Pluto's vast distance. These data sets included high-resolution photographs, topographic information, surface ice spectra, atmospheric profiles, and satellite data. Pluto has 5 known moons. Chiron, the largest, followed by the smaller Styx, Nix, Kerberos, and Hydra. One of the most remarkable discoveries from New Horizons was the breathtaking panoramic view of Sputnik Planitia, an unofficial but widely used name, the towering ice mountains several kilometers high, deep canyons on Charon, and the mysterious wavy surface structures. New Horizons effectively completed the first, and likely the only visit to Pluto for many decades. After completing its primary mission to study the dwarf planet, the probe continued its journey into the Kuiper Belt, where in 2019 it performed a flyby of the object Arrokoth, previously known as Ultima Thule. At present, no major space agency has concrete plans for another mission to Pluto. However, space exploration enthusiasts have proposed the idea of an orbital station or even a lander. Given the immense technological and financial challenges involved, such a project could only be realized in the distant future. For now, astronomers continue to collect additional data using telescopes such as Hubble and ground-based observatories equipped with adaptive optics. These observations help track surface changes as Pluto moves along its orbit. Scientists predict that as Pluto drifts farther from the Sun, more nitrogen will freeze onto its ice plains, while a portion of its tenuous atmosphere will settle onto the surface as frost. Looking ahead, if humanity develops more advanced propulsion systems, such as improved nuclear or ion drives, we might one day send a spacecraft capable of entering Pluto's orbit, similar to NASA's Cassini mission to Saturn. Such an orbital station could spend years studying Pluto's geological details, the structure of its potential subsurface ocean, atmospheric dynamics, and interactions with the solar wind at the edge of the solar system. However, for now, these remain ambitious ideas requiring groundbreaking technological advancements and vast financial investments. Despite decades of research, Pluto still holds countless mysteries. Once considered the 9th planet of the solar system, later demoted to a dwarf planet, Pluto remains an essential subject of study. Neither the debate over its classification nor its remoteness and small size diminish its importance. Pluto showcases incredibly young regions on its surface, massive mountains composed of water ice, strange dark terrains, and distinct geological features that may still be evolving. The entire Pluto-Charon system is filled with unusual characteristics. The center of their mutual orbit lies in space between them, and Pluto's 5 moons resemble a chaotic cosmic ballet. Another fascinating aspect is Pluto's ultra-thin atmosphere. Despite being so tenuous that it borders on a vacuum, it still produces twilight effects and a delicate haze. This dynamic breathing of Pluto's nitrogen atmosphere, freezing and sublimating depending on its position in orbit, reveals that even at the outermost reaches of the solar system, seasonal changes can occur. Although these changes unfold on an extremely long timescale, Pluto's orbit takes 248 Earth years to complete. They highlight the contrast of this distant world. Pluto provides a window into the processes occurring beyond Neptune, in a region populated by hundreds or even thousands of other icy bodies. By studying it, we gain key insights into the broader Kuiper Belt, a region that significantly influences the dynamics of the solar system's outermost regions. Furthermore, Pluto is an excellent example of how a body smaller than our moon can retain internal heat and exhibit geological activity, likely due to tidal interactions with Charon and possibly even radioactive decay in its rocky core. If a subsurface ocean does exist beneath Pluto's icy crust, it would be an astonishing discovery. We are already familiar with subsurface oceans on the giant moons of Jupiter and Saturn, but finding one on a small, distant dwarf planet would challenge our expectations about where liquid water can persist in the solar system. Looking toward the future, we can hope that the excitement generated by New Horizons will eventually lead to new missions. Perhaps one day we will develop a spacecraft capable of slowing down near Pluto and entering its orbit for long-term exploration. Such a mission could allow us to monitor how Tombaugh Regio's heart shifts, grows, or shrinks with the seasons, how icy volcanoes slowly erupt frozen materials, and how Pluto's weak magnetic field, if it exists, interacts with the solar wind. Additionally, scientists would love to understand how Charon influences Pluto's tidal forces and internal activity, whether Pluto once had a vast subsurface ocean, and how its thin atmosphere interacts with the surrounding environment. All of these questions deserve attention, as answering them would expand our understanding of how the solar system's outermost planets and dwarf planets behave beyond Neptune's orbit. Despite its small size and vast distance from the Sun, Pluto is a truly unique celestial body. It exhibits striking contrasts, from frozen nitrogen plains to towering water ice mountains, from unpredictable cryovolcanism to seasonal atmospheric changes. Its exploration was made possible by visionary projects like New Horizons and the immense enthusiasm of the scientific community, and the probe's 2015 flyby exceeded all expectations. Although life on Pluto is highly unlikely due to its extreme conditions, temperature, pressure, and lack of sunlight, the planet itself provides invaluable insights into the evolution of icy objects originating from the depths of the Kuiper Belt. Moreover, it offers a new perspective on planetary formation and transformation processes across the solar system. In this sense, Pluto's exploration serves a broader purpose: understanding how different kinds of worlds, large and small, hot and cold, massive and tiny, shape the overall structure of our planetary system. If you have any thoughts on what else Pluto might be hiding, or whether another mission should be sent to explore it, feel free to share in the comments. Public interest is one of the driving forces behind science and technology. Perhaps in the future, inspired by the incredible images and discoveries from New Horizons, we will see an even more ambitious project, such as an orbital station that lingers in the Pluto-Charon system for years, closely tracking seasonal and geological changes occurring billions of kilometers from the Sun. For now, let's appreciate the astonishing world that has already been revealed to us thanks to New Horizons, and remember that the universe is filled with countless discoveries waiting to be made. Stay connected as space exploration continues, offering us new insights into the most distant corners of the solar system. Far beyond the familiar orbits of Jupiter and Saturn, and even beyond the enigmatic ice giants Uranus and Neptune, lies a cold and enigmatic frontier, an immense belt populated by countless icy worlds drifting silently in perpetual darkness. This mysterious region, known as the Kuiper Belt, holds secrets that have fascinated astronomers for decades and continues to captivate our imagination today. The Kuiper Belt is a massive ring-shaped region located beyond the orbit of Neptune, beginning approximately 30 astronomical units, AU, from the Sun, where 1 AU is equal to the distance from the Earth to the Sun, and stretching out to about 55 AU and beyond. For comparison, the orbit of Pluto, which is part of this belt, ranges between 30 and 49 astronomical units. At these tremendous distances, sunlight is only a faint glimmer, more than 1,000 times weaker than what we experience on Earth. Here, temperatures plummet to minus 220 degrees Celsius and lower, and these frozen worlds drift silently through space, occasionally disturbed by distant gravitational interactions. This distant region was named in honor of astronomer Gerard Kuiper, who in 1951 first hypothesized the existence of icy objects beyond Neptune. However, Kuiper himself doubted whether such objects would still exist, believing they would have long since dispersed under gravitational influences. Surprisingly, the first Kuiper Belt object was only discovered in 1992, decades after Kuiper's death, by astronomers David Jewett and Jane Liu. Their observations of a faint object orbiting beyond Neptune opened a new chapter in the study of our solar system and changed our understanding of its formation forever. Since this initial discovery, more than 2,000 Kuiper Belt objects, KBOs, have been identified, with countless others estimated to lurk undetected in the darkness. The belt's population is believed to number in millions, possibly billions, ranging from small icy fragments just a few meters wide to enormous dwarf planets comparable in size to Pluto. Among the known objects, Pluto remains the most famous, reclassified in 2006 from a planet to a dwarf planet, precisely because astronomers realized it was just one of many similar bodies inhabiting the Kuiper Belt. What makes the Kuiper Belt so intriguing is its diversity. Unlike the rocky asteroids found closer to the Sun, these distant worlds are predominantly icy, composed mainly of frozen water, ammonia, methane, and other volatile compounds. Their icy surfaces often have dark, reddish hues due to the chemical reactions triggered by ultraviolet radiation from the Sun, which breaks down complex organic molecules. These organic-rich surfaces make Kuiper Belt objects incredibly valuable to scientists studying the earliest history of our solar system. Each icy fragment preserves a frozen snapshot of the primordial nebula that gave birth to the Sun and planets, offering us precious insights into our cosmic past. Among the numerous inhabitants of the Kuiper Belt, there are several notable objects that astronomers have studied extensively. One of the largest and most fascinating is Eris, discovered in 2005. Slightly smaller in diameter than Pluto, but significantly denser and more massive. Eris orbits the Sun at an astounding distance of about 68 astronomical units at its farthest point. Its discovery was so significant that it directly prompted astronomers to redefine the concept of planet, ultimately leading to Pluto's reclassification. Another intriguing world is Haumea, a rapidly spinning dwarf planet shaped like an elongated ellipsoid. Haumea rotates so swiftly, completing a full spin approximately every 4 hours, that it has become distinctly flattened. Additionally, Haumea possesses at least 2 moons and even a thin ring system, marking it as a unique celestial object in our solar system. Yet another remarkable object is Makemake, which was discovered shortly after Eris. Its surface reflects sunlight with remarkable brightness, hinting at the presence of fresh, reflective ice layers. Interestingly, astronomers recently found evidence suggesting Makemake might host a thin atmosphere when it passes closer to the Sun, an atmosphere that freezes and collapses onto its surface as it moves further away. The famous Pluto, once considered our 9th planet, is now recognized as the Kuiper Belt's most famous dwarf planet. The groundbreaking mission New Horizons, launched in 2006, finally arrived at Pluto in July 2015 after traveling nearly 5 billion kilometers. It sent back extraordinary high-resolution images, revealing a diverse and active world with mountains made of water ice, vast nitrogen glaciers, complex geology, and even possible signs of subsurface liquid oceans. New Horizons revelations provided humanity's first close-up view of the Kuiper Belt and revealed that even in this frozen realm, geological processes remain dynamic and surprisingly active. Further demonstrating the diversity of this region, the Kuiper Belt also contains peculiar binary systems, pairs of similarly sized icy objects orbiting a common center of gravity. One striking example is Arikot, a unique contact binary visited by New Horizons in 2019. Its shape resembles 2 pancake-like lobes gently fused together, hinting that it formed from the gentle collision and merger of 2 smaller bodies billions of years ago. This intriguing object represents the oldest and most primitive celestial body ever explored, preserving critical clues about planet formation processes. The origin and structure of the Kuiper Belt remain a subject of lively scientific discussion. Astronomers believe that gravitational influences, primarily from Neptune and Jupiter, shape this distant ring of icy objects. Computer models suggest that as the giant planets shifted their orbits early in the solar system's history, countless icy planetesimals were ejected outward into the current Kuiper Belt region. This turbulent era, known as the Late Heavy Bombardment, might also have led to numerous impacts that scarred surfaces of moons and planets closer to the Sun, potentially even delivering water and organic compounds to early Earth. But perhaps the most tantalizing mystery associated with the Kuiper Belt is the elusive Planet 9. Some astronomers hypothesize that an unseen, massive planet, possibly a super-Earth, is orbiting far beyond Neptune, influencing the orbits of several distant Kuiper Belt objects. While direct evidence remains elusive, ongoing observations continue to search for this theoretical world, which would fundamentally alter our understanding of the solar system's layout and evolution. Currently, the exploration of the Kuiper Belt remains limited. However, future missions may include robotic spacecraft equipped with advanced instruments designed for long-term observations, or even landers that could touch down on icy worlds to collect samples directly. Spectroscopic analysis, radar mapping, and detailed imaging are just some of the powerful methods planned for these future explorations. As technology advances, we can expect to discover countless new celestial objects, revealing yet more secrets hidden within this remote frontier. The Kuiper Belt, despite its distant and icy quietness, continues to fascinate humanity because it holds answers to fundamental questions about our own origins and the history of our solar system. By studying these primitive worlds, we look billions of years into the past, exploring the building blocks that created Earth and, potentially, provided the materials necessary for life itself. It reminds us that our solar system is a complex and ever-changing environment filled with phenomena we are only beginning to comprehend. Perhaps somewhere deep within these frozen realms await answers to mysteries we have not yet dared to ask. Every new discovery brings us one step closer to understanding not only the history of our planetary neighborhood, but also the broader cosmic story. Who knows what incredible secrets still lie buried in the shadows of the Kuiper Belt? As we continue to reach out further into space, we are certain of one thing: the universe has many more surprises to reveal, and every new mission holds the promise of discoveries that may forever change our view of our place among the stars. For centuries, astronomers have searched the night sky for celestial objects that might reveal the secrets of the cosmos. Some stars shine brilliantly, dominating constellations with their radiant glow, while others are nearly invisible to the naked eye. Silent wanderers moving through space unnoticed by early stargazers. One such star, a dim, unassuming red dwarf known as Barnard's star, has captured the imagination of scientists and dreamers alike. Despite being one of the closest stars to Earth, Barnard's star remained unknown for most of human history. Its true significance only became apparent in the 20th century when astronomers discovered its astonishing speed across the sky. But the real mystery lies in what orbits it. A world that defies expectations, a frozen, windswept exoplanet that may hold the key to understanding planets around red dwarfs. What makes Barnard's star unique? Could its planet be a hidden sanctuary for life, despite its harsh conditions? And why does this ancient star continue to fascinate scientists more than a century after its discovery? Let's embark on a journey to uncover the mysteries of one of the most enigmatic stars in our cosmic neighborhood. For most of human history, Barnard's star remained invisible to astronomers. Too faint to be seen with the naked eye, it escaped notice until E. Barnard, an American astronomer, identified it in 1916. What he discovered shocked the scientific community. This unremarkable red dwarf was moving across the sky faster than any other known star. Its apparent motion, known as proper motion, is the highest of any star relative to the Sun. Barnard's star shifts by an incredible 10.3 arc-seconds per year, meaning that in just a few centuries, it noticeably changes position against the background of distant stars. This rapid motion suggests that Barnard's star is on a journey, perhaps an ancient traveler from another region of the galaxy, making its way through the cosmic void. At just 5.96 light-years away, Barnard's star is the second closest known star system to Earth, surpassed only by Alpha Centauri. This proximity makes it an ideal candidate for study, especially as astronomers seek to understand the worlds that orbit red dwarf stars. But the true excitement began when scientists turned their attention to what might be hidden within Barnard's system: an exoplanet orbiting this ancient star. For decades, astronomers suspected that Barnard's star might host planets. In the 1960s, astronomer Peter van de Kamp claimed to have detected a massive world orbiting it, but later analysis showed his findings to be incorrect. The mystery of whether Barnard's star had planets remained unsolved until 2018, when a breakthrough occurred. Using precise radial velocity measurements from the Carmines and HARP spectrographs, astronomers detected a subtle wobble in the star's motion. This was the unmistakable signature of an orbiting planet. Named Barnard's star B, this exoplanet is classified as a super-Earth, a rocky world larger than Earth but smaller than Neptune. The planet orbits Barnard's star once every 233 days, placing it at a distance where liquid water is unlikely to exist. Due to the faint light from its red dwarf star, Barnard's star B is a cold and frozen world, with surface temperatures estimated to be around minus 170 degrees Celsius or minus 274 degrees Fahrenheit. If this planet has an atmosphere, it might offer some protection against the extreme cold. But without greenhouse gases, it would be an icy desert, a world of perpetual twilight under the dim glow of its ancient sun. Despite its harsh conditions, Barnard's star B is an exciting discovery. It is one of the closest known exoplanets to Earth, and its existence hints at the possibility of more planets in the system waiting to be found. Could there be other, smaller worlds hidden in its orbit? And if so, could any of them be warm enough to support life? One of the most intriguing aspects of Barnard's star is its age. While our sun is around 4.6 billion years old, Barnard's star is estimated to be at least 10 billion years old, more than twice the age of our solar system. It formed when the Milky Way was still young, at a time when many of the heavier elements that make up planets and life were scarce. As a red dwarf, Barnard's star has burned through its hydrogen fuel at an incredibly slow rate, allowing it to survive for billions of years. Unlike massive stars that explode as supernovae after only a few million years, red dwarfs can live for trillions of years, meaning Barnard's star will outlive the sun by an unimaginable time span. Its ancient age raises a fascinating question. If planets existed around Barnard's star for billions of years, could life have had enough time to develop? And if so, what might it look like on a world locked in an eternal winter? At first glance, Barnard's star B seems like an unlikely place for life to exist. With temperatures far below freezing, the planet would appear to be a barren wasteland, locked in an icy grip. However, life has a way of surviving in the most extreme environments. On Earth, microorganisms known as extremophiles thrive in deep-sea hydrothermal vents, under Antarctic ice sheets, and in frozen deserts. If Barnard's star B has geothermal activity, it is possible that subsurface oceans could exist beneath layers of ice, similar to Europa or Enceladus in our own solar system. Another possibility is that the planet has retained an atmosphere rich in carbon dioxide or methane, which could create a greenhouse effect, trapping heat and making conditions slightly more hospitable. While this scenario is purely speculative, it opens the door to intriguing possibilities about the adaptability of life in the universe. Imagine setting foot on the surface of Barnard's star B. The sky above would be a deep red twilight as the dim light of Barnard's star struggles to illuminate the frozen landscape. The sun in the sky would be just 1/100th as bright as our sun, casting an eerie glow across the icy plains. The surface would likely be covered in frozen carbon dioxide or nitrogen ice, sculpted by alien winds. The air, if there is any, would be unbreathable, requiring explorers to wear protective suits. If the planet had active volcanism, geysers of water or methane might occasionally erupt from beneath the ice, creating surreal landscapes reminiscent of the geysers on Saturn's moon Enceladus. Would there be any signs of life deep below, in hidden, warm pockets of liquid water? We may not know for certain until we send probes or more advanced telescopes to uncover the truth. Because of its proximity, Barnard's star is an excellent target for future exploration. Several upcoming telescopes, including the James Webb Space Telescope, will study exoplanets in detail, analyzing their atmospheres for signs of habitability. If Barnard's star B has an atmosphere, these instruments may be able to detect water vapor, methane, or even oxygen, potential biosignatures that could indicate the presence of life. Additionally, projects like Breakthrough Starshot aim to develop tiny laser-powered probes that could travel to nearby star systems, including Barnard's star. These spacecraft, no larger than a microchip, could reach speeds of 20% the speed of light, making it possible to send data back within a few decades. Such missions could provide direct images of Barnard's star B, allowing us to see its surface for the first time and determine whether it is a frozen wasteland or something far more mysterious. Barnard's star is more than just a fast-moving red dwarf. It is a gateway to the unknown. It represents the possibility of planets in ancient systems, the search for life in extreme conditions, and the future of interstellar exploration. Though it is cold, old, and dim, Barnard's star and its lone planet may help answer some of the greatest questions in astronomy. Does life require warmth and sunlight? Or can it exist in hidden, frozen worlds? What secrets do ancient stars hold about the early universe? As technology advances, humanity is on the verge of unlocking these mysteries. Perhaps one day explorers from Earth will set foot on the icy plains of Barnard's star B, gazing up at its crimson sky and knowing they have touched a world beyond the sun. The night sky has always fascinated humankind. Since ancient times, our ancestors gazed at the stars, wondering about their nature and whether life might exist beyond our small planet. Over the centuries, as science progressed, we unraveled many cosmic mysteries, yet countless more remain unanswered. Among the closest and most intriguing of these celestial objects is the Alpha Centauri system, a stellar trio that might one day become humanity's first destination beyond the solar system. Despite its proximity of just 4.37 light-years, Alpha Centauri remains an enigmatic and complex system, containing at least 3 known stars and possibly several undiscovered exoplanets. Could any of them harbor life? What secrets do these neighboring suns hold? As our telescopes peer deeper into this stellar system, new findings continue to reshape our understanding of the cosmos. Today, we embark on a journey to uncover the mysteries of Alpha Centauri, exploring its past, present, and future as a potential second home for humanity. The story of Alpha Centauri begins not with modern astronomers, but with ancient stargazers who mapped the heavens without telescopes. Visible only from the southern hemisphere, the 2 brightest stars of Alpha Centauri A and Alpha Centauri B, were observed by indigenous cultures long before European explorers ever set foot in the southern hemisphere. However, it was in 1689 that Jean Richaud, a French Jesuit priest and astronomer, first identified Alpha Centauri as a binary star system. His observations, conducted from Pondicherry, India, paved the way for centuries of research. Later in 1915, the 3rd member of the system, Proxima Centauri, was discovered by the Scottish astronomer Robert Innes, marking a groundbreaking revelation. This was the closest star to the Sun. Since then, Alpha Centauri has been a prime target for astronomical observations. From early optical telescopes to the sophisticated space-based instruments of today, astronomers have sought to understand its composition, its planetary potential, and even the possibility of extraterrestrial life. At first glance, Alpha Centauri appears as a single bright star in the constellation Centaurus. However, it is actually a 3-star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Each of these stars plays a distinct role in shaping the system's dynamics. Alpha Centauri A is a G-type main sequence star, similar to our Sun but slightly larger and more luminous. It shines with a warm yellowish hue, with a surface temperature of around 5,800 Kelvin. Its slightly greater mass means it burns its nuclear fuel at a faster rate, but it is expected to remain stable for billions of years. Alpha Centauri B, on the other hand, is a K-type star, slightly cooler and smaller than the Sun. It emits a more orange-colored light and has a lower energy output, making it dimmer than its companion. Despite these differences, both stars orbit each other in a complex elliptical dance, completing a full revolution every 79.9 years. But the most fascinating and mysterious member of the trio is Proxima Centauri, a red dwarf. This small, dim star is often overlooked, yet it is the closest star to Earth beyond our Sun. It lies about 0.21 light-years from the central Alpha Centauri binary and takes hundreds of thousands of years to orbit them. Red dwarfs like Proxima are known for their longevity, burning their hydrogen fuel so slowly that they can live for trillions of years. However, they are also infamous for their violent flares, which can dramatically impact any nearby planets. For decades, astronomers have speculated about the presence of planets orbiting Alpha Centauri. Given the system's proximity, discovering an Earth-like world here would be a monumental breakthrough. It would mean that interstellar travel might one day be within our reach. The first significant breakthrough came in 2016, when scientists confirmed the discovery of Proxima b, an exoplanet orbiting within Proxima Centauri's habitable zone. This planet, roughly 1.3 times the mass of Earth, completes a full orbit around its star every 11.2 days. While this sounds promising, Proxima b's environment is likely harsh due to its parent star's intense stellar flares. If it has an atmosphere or strong magnetic field, it might retain conditions favorable for life. However, more research is needed to determine its true habitability. In recent years, astronomers have hinted at the existence of other planets in the system. Proxima Centauri c, a possible super-Earth or mini-Neptune, was detected in 2020, but its habitability remains doubtful due to its greater distance from the star. Meanwhile, speculation continues about whether Alpha Centauri A or B could harbor planets, perhaps even Earth-like ones, though no definitive evidence has been found. Upcoming space telescopes, such as the James Webb Space Telescope and the European Extremely Large Telescope, are expected to shed more light on this question. If a planet is discovered in the habitable zone of Alpha Centauri A or B, it would be the most promising candidate for interstellar exploration. Let's imagine for a moment that humanity has developed the technology to travel to Alpha Centauri. What would an astronaut see upon arrival? If approaching from the outer edges of the system, Proxima Centauri would be the first landmark. It would appear as a dim, reddish dot, barely illuminating its surroundings. As our spacecraft moves closer to Alpha Centauri A and B, the view would become spectacular. These twin stars shine brightly, dominating the sky. If there were habitable planets orbiting them, they would experience an unusual celestial display. Two suns casting golden and orange glows over alien landscapes. If one of these planets harbored life, what might it look like? Would it resemble Earth, with vast oceans and green continents? Or would it be an entirely different world, shaped by an environment unlike anything we know? The answers to these questions remain unknown, but with advancing space technology, we might not have to wait long to find out. Alpha Centauri has long been a subject of fascination in science fiction, from books and movies to video games. But beyond fiction, serious efforts are underway to make interstellar exploration a reality. One of the most ambitious projects is Breakthrough Starshot, an initiative aiming to send small, laser-powered probes to the Alpha Centauri system within the next few decades. Using ultra-thin, light-propelled sails, these miniature spacecraft could travel at 20% of the speed of light, reaching the system in about 20 years. If successful, this mission would mark the first human-made objects to travel beyond the solar system at such high speeds. The data collected could revolutionize our understanding of planetary systems beyond our own. Moreover, with advancements in AI, quantum computing, and autonomous spacecraft, humanity may one day send larger crewed missions to Alpha Centauri. The biggest challenges, radiation exposure, propulsion technology, and self-sustaining habitats, remain unsolved. But given enough time, these obstacles may be overcome. Understanding Alpha Centauri is not just about satisfying scientific curiosity. It is a necessary step in humanity's long-term survival. Our sun, though stable, will eventually exhaust its nuclear fuel, forcing us to look outward for new homes. Interstellar travel may seem like a distant dream, but every breakthrough in astronomy, physics, and engineering brings us closer to making it a reality. Furthermore, the search for exoplanets in Alpha Centauri may help us answer one of the most profound questions. Are we alone in the universe? If life can arise elsewhere, Alpha Centauri is one of the best places to look for it. Even if we do not find extraterrestrial civilizations, The study of planets in this system will teach us about planetary formation, habitability, and the delicate balance that makes Earth so special. Alpha Centauri stands as a beacon of exploration, an emblem of our cosmic curiosity and ambition. It is a system rich with mysteries, 3 stars, potentially habitable planets, and the closest stepping stone to the rest of the galaxy. While reaching it remains a formidable challenge, the first steps are already being taken. Perhaps one day, long after our first pioneers set foot on Mars, a new generation of explorers will embark on the greatest journey of all, an interstellar voyage to Alpha Centauri. Whether as scientists, dreamers, or future travelers among the stars, humanity's connection to its nearest stellar neighbor will only deepen with time. The universe is vast, and Alpha Centauri is but the first step. What awaits beyond? Only time will tell. When we look up at the night sky, we see more than just stars. We see history, mythology, science, and mystery woven into tiny points of light. Some stars blink faintly in the distance, cold and ancient, barely brushing the darkness. Others blaze like celestial lighthouses, dominating the heavens with their brilliance. And among them all, Sirius stands apart, the brightest star in our night sky, a luminous beacon that has captured human imagination for millennia. But behind its dazzling light lies a story far deeper and more complex than mere brightness. Sirius is not just a star, it's a double system, a cosmic enigma, and a stellar paradox. It hides a white dwarf, the ghost of a long-dead star, locked in gravitational dance with a shining, massive companion. It is both old and new, radiant and fading, ordinary and extraordinary. Let's travel across time and space to unravel the secrets of Sirius, the blazing heart of the winter sky, and explore the mysteries that have surrounded it for thousands of years. From ancient civilizations to modern telescopes, Sirius has never gone unnoticed. It has been revered, measured, feared, and studied. Known to the ancient Egyptians as Sopdet and to the Greeks as Sirios, meaning scorching or glowing, this star held great importance in many early cultures. To the Egyptians, the heliacal rising of Sirius, when it reappeared in the dawn sky after being hidden behind the sun, marked the start of the annual Nile flood and the beginning of the new year. It was so crucial that entire religious calendars were based around it. In Dogon mythology in West Africa, Sirius was believed to be part of a binary system long before modern science confirmed it, a fact that still sparks fascination and speculation today. Sirius has always been more than a bright light in the night. For ancient astronomers, it was a cosmic marker, a clock in the sky, a calendar for life on Earth. Sirius resides in the constellation Canis Major, the Great Dog, and is often called the Dog Star. At a distance of about 8.6 light-years, it is one of our closest stellar neighbors, which contributes to its incredible brightness in our sky. But brightness is not just about proximity. Sirius A, the main star we see, is roughly 25 times more luminous than the Sun and about twice as massive. It shines with a spectral type A1V, meaning it's a white-blue main sequence star with a surface temperature of around 9,940 degrees Celsius, 17,900 degrees Fahrenheit. That's nearly twice as hot as our Sun. The name Sirius is derived from the Greek Sirios, glowing or scorching, a name it earned not just for its radiance, but for its fiery role in myth and season. But Sirius is not one star, it is two. And the second member of this cosmic pair, though invisible to the naked eye, is one of the most remarkable stellar remnants in our cosmic neighborhood. Orbiting Sirius A every 50.1 years is Sirius B, a star that no longer shines with its own light. This companion was once larger and more massive than Sirius A itself. But it ran out of nuclear fuel long ago, collapsing into a tiny dense sphere, the remnant of a star's final breath. What remains is a white dwarf, about the size of Earth but with a mass nearly equal to that of the Sun. To put it in perspective, a teaspoon of Sirius B's matter would weigh around 5 tons on Earth. Sirius B is one of the first white dwarfs ever discovered, and it was also the first whose existence was predicted before it was seen. Astronomers noticed that Sirius A exhibited a slight wobble in its motion, indicating the gravitational tug of an unseen companion. In 1862, American astronomer Alvin Clark finally observed this ghostly object through his telescope, the same year the U.S. Civil War began. Despite its dead nature, Sirius B is a fascinating object of study. It shines not from nuclear fusion, like regular stars, but from the residual heat left over from its fiery past. Over billions of years, it will continue to cool, becoming darker and colder, fading into a theoretical black dwarf, a state the universe has not existed long enough to produce. Sirius A is a hot, white-blue main sequence star with a diameter about 1.7 times that of the Sun. Its mass is approximately 2.1 solar masses, and its energy output is much greater, yet its life expectancy is significantly shorter. While the Sun has a lifespan of around 10 billion years, Sirius A is expected to last only around 1 to 1.5 billion years in its current state. Inside Sirius A, hydrogen is fusing into helium in a core reaching over 20 million degrees Celsius. Convection and radiation carry this energy outward, causing the star to glow with a brilliant white light tinged with blue. Sirius B, in contrast, is a degenerate object, a stellar corpse made entirely of electron-degenerate matter. Though it's only 12,000 kilometers in diameter, its gravity is intense, and its surface temperature can reach 25,000 Kelvin, much hotter than Sirius A. But without fusion, it is a star running only on thermal inertia. Together, this stellar duo paints a stark contrast: youth and age, energy and entropy, light and shadow. Sirius A and B orbit each other in a highly elliptical path, with an average separation of 20 astronomical units, roughly the distance between the Sun and Uranus. However, their orbital distance varies from about 8 to 31 astronomical units, creating complex gravitational interactions. The precise nature of their orbit has allowed scientists to test predictions of Einstein's general theory of relativity. In fact, by observing the motion of Sirius B in particular, astronomers have been able to detect relativistic effects like gravitational redshift, a phenomenon where light escaping the intense gravity of the white dwarf loses energy, becoming slightly redder. This makes Sirius not just a visual wonder, but a natural laboratory for physics. For years, scientists and dreamers have wondered, could planets orbit Sirius? Could a civilization exist on a world bathed in the light of the brightest star in our sky? So far, no planets have been confirmed around Sirius A or B. However, the intense glare of Sirius A makes detecting smaller objects in its vicinity extremely difficult. The gravitational interactions between the two stars may also make stable planetary orbits difficult, at least within a few AU of the pair. That said, recent developments in infrared and high-contrast imaging are enabling astronomers to look for giant exoplanets in more complex systems. Some speculative claims have been made about faint infrared sources near Sirius, but no credible detection has held up under scrutiny yet. Still, the search continues, and even if planets are absent, the question of life around binary stars remains one of the most intriguing in modern astronomy. Sirius is not only important to scientists, it holds a special place in the cultural history of humanity. To the Aboriginal Australians, it represented a hunter or an eagle. The Polynesians used it for navigation across the Pacific. In Japan, it is known as aoboshi, and in ancient China, it formed part of the celestial wolf. In the western sky, Sirius marks the nose of Canis Major, the loyal dog following Orion across the heavens. On winter nights in the northern hemisphere, it is a dazzling presence, unmistakably the brightest point of light in the sky. 25 times more luminous than the Sun, its brilliance undimmed by distance. Sirius even inspired the term "dog days of summer," referring to the time when it rises with the Sun, an association born from ancient belief that Sirius added heat to our star, causing the sweltering midsummer weather. Even today, Sirius remains at the heart of cosmic mystery. Some alternative theorists have pointed to ancient Dogon myths and wondered how such early cultures knew of Sirius's binary nature. While the claims remain controversial and unverified, they do speak to the enduring allure of this star system. Modern missions such as Gaia and ground-based adaptive optics telescopes continue to study the Sirius system with astonishing precision. Gaia has provided more accurate measurements of Sirius's motion and distance than ever before, while other observatories search for faint planetary companions or debris disks. Sirius is more than just a star. It is a symbol of time, a cosmic clock, a testing ground for physics, and a cultural beacon that has inspired humans across millennia. It is the brightest star, yes, but also one of the most mysterious. Its brilliant light pierces the cold of winter nights. Its history stretches back into myth. Its physical properties challenge our understanding of stellar evolution. And its future remains uncertain, wrapped in the long timelines of the cosmos. As we look up and see Sirius shimmering overhead, perhaps we are also looking into a mirror, one that reflects not only the nature of stars, but our own longing to understand the universe we inhabit. And somewhere in that longing, in the quiet between stars, the dog star watches. Imagine looking up at a night sky bursting with stars, each a tiny beacon set against the vast black canvas of space. In centuries past, people believed our own sun, accompanied by its retinue of planets, might be a rare configuration, perhaps even the only one. But the era of exoplanet discovery, flourishing across the last few decades, has rewritten that assumption entirely. Our galaxy teems with stars, many of them harboring worlds of all shapes and sizes. Super-Earths larger than our planet, but smaller than Neptune. Hot Jupiters skimming perilously close to their scorching stars. Rocky planets locked in tidal embraces, and so much more. Even with such a bounty of extraordinary findings, the TRAPPIST-1 system stands out as a dazzling treasure trove. In a single faint red star, astronomers have discovered 7 rocky planets, each roughly Earth-sized, 3 of which reside in that most coveted region known as the habitable zone. This configuration has captured the imagination of scientists and dreamers alike, tempting us with the possibility that at least one of those 7 siblings might harbor the conditions needed for liquid water, or perhaps even life. The first whisper of this system's existence came from a modest Belgian-operated robotic telescope, the TRAPPIST facility in Chile. Designed initially for comet surveys and exoplanet transits, this unassuming instrument turned its gaze on a dim star in the constellation Aquarius, about 40 light-years from Earth. What it found there, starting around 2015 and confirmed in 2016, took the astronomical community by storm. At first, astronomers noted evidence for 3 planets passing in front of that star, periodically blocking a fraction of its feeble light. These signals, known as transits, are a gold standard for exoplanet detection. If a planet is aligned just so, each time it crosses the star's face, it creates a tiny regular dip in brightness. Further study with the Spitzer Space Telescope, supplemented by ground-based observations, soon revealed that the star actually hosts 7 transiting planets. Overnight, TRAPPIST-1 became a sensation, a living testament to the improbable diversity of planetary systems that can arise around even the smallest, dimmest suns. The star at the center of this cosmic story is but a fraction of the sun's mass and brightness. A red dwarf on the cusp of not being a star at all, barely massive enough to sustain the nuclear fusion of hydrogen. Astronomers refer to it as an ultra-cool dwarf with a surface temperature of roughly 2,500 Kelvin, far below our sun's nearly 5,800 Kelvin. In terms of mass, TRAPPIST-1 weighs in at only about 9% that of the sun. You could stack more than 10 of these tiny stars to match the sun's radius. Its luminosity is so faint that, from Earth, it cannot be seen with the naked eye. And yet, in that quiet corner of space, It has managed to forge a family of 7 planets that somehow ended up aligning their orbital planes perfectly from our perspective, letting us witness each transit as it happens. That improbable geometry offers a rare chance to measure these worlds in detail. Each dip in brightness gives clues to a planet's size, and subtle variations in transit timings caused by the gravitational pushes and pulls of other planets reveal their masses. Wrapped around this cool star, the 7 siblings revolve at breakneck speeds compared to our familiar Earth year. One of them completes a lap in about a day and a half, another in just over 2 days, and the outermost in less than 3 Earth weeks. So tightly are they packed that the entire system could fit well within the orbit of Mercury in our solar system. A star so dim might seem to offer little in the way of illumination, yet because the planets are nestled so close, some of them receive levels of stellar flux that could, under the right conditions, sustain liquid water on their surfaces. The trio that has generated the most excitement sits in or near the so-called habitable zone, where stellar irradiation is neither too fierce nor too feeble. If their atmospheres are suitably dense, and if they possess protective magnetic fields to guard against stellar flares, they might see water pooling on their surfaces or swirling in their air as clouds, one of the cornerstones for life as we know it. From the earliest telescopes that homed in on TRAPPIST-1, scientists have been racing to understand not just how many planets are present, but what these worlds might actually be like. One immediate clue comes from measuring the planet's radii and masses, which in turn yield densities, crucial for distinguishing a rocky Earth-like composition from a gas-dominated one. Thanks to painstaking analyses of transit timing variations, we know these planets likely lack the sort of thick hydrogen-helium envelopes that define Neptune-like bodies. Instead, many appear to be truly terrestrial, with densities pointing to iron cores and silicate mantles. Some are even suspected of harboring substantial amounts of water. Their compact arrangement and near-resonant orbits also hint at a nuanced formation scenario. It's plausible that they coalesced farther out in the star's protoplanetary disk, rich in ices, then migrated inward as the system evolved. The question that has seized public imagination is habitability. On Earth, life thrives thanks to a delicate interplay of atmosphere, temperature, liquid water, magnetic fields, and geologic activity. If the TRAPPIST-1 worlds host the right combination of these elements, they could, in the theory, support microbial life, or at the very least, Earth-like climates. But an ultra-cool dwarf star, for all its gentle brightness, can be temperamental in other ways. M-dwarf stars are known to produce flares, bursts of charged particles and radiation that can wear away a planet's atmosphere over time if there is no robust magnetic field to deflect that onslaught. The closeness of the TRAPPIST-1 planets amplifies that risk. Tidal locking, another likely side effect of orbiting so close, means that one hemisphere may constantly face the star, while the opposite side remains in perpetual darkness. Without effective circulation of heat through an atmosphere, the day side might be scorching, the night side sub-zero. Yet climate models do suggest that a sufficiently thick and well-balanced atmosphere could transport warmth around the planet, allowing stable conditions at the terminator region or even across the entire surface, if cloud formation reflects just enough of the incoming radiation. Astronomers have been eager to uncover whether these scenarios hold any truth. Observations with the Hubble Space Telescope offered early hints by analyzing the starlight that filters through the outer edges of each planet's atmosphere during transit. If any planet were encased in a huge blanket of hydrogen gas, it would reveal itself in the spectrum. But that does not appear to be the case here, at least not for the innermost worlds. More definitive answers are now being sought by the James Webb Space Telescope, which has the precision in the infrared needed to detect molecules such as carbon dioxide, methane, oxygen, and water vapor. By measuring subtle dips in brightness at specific wavelengths, scientists can glean a planet's chemical fingerprints. Even the detection of clouds or a global ocean might lie within reach given enough observational time and a bit of luck. It is a difficult enterprise requiring extremely careful calibration of instruments, but the prize is tantalizing, a genuine reading of the atmospheres enveloping these Earth-sized worlds. History shows how swiftly TRAPPIST-1 evolved from a faint, overlooked star to a prime subject of investigation. In the mid-2010s, ground-based transit surveys discovered a handful of planetary signals around it. Follow-up with NASA's Spitzer Space Telescope, designed to examine cosmic infrared light, opened up a more extended, uninterrupted view, revealing the presence of 7 planets. Then came the wave of Hubble and ground-based spectrographic follow-ups, refining parameters bit by bit. Across the globe, telescopes collaborated to measure minute changes in transit curves. Each fleeting dip offered another puzzle piece for planetary astronomers to place in the mosaic. And now that James Webb is operational, TRAPPIST-1 sits high on the priority list of cosmic targets, representing a laboratory for everything we hope to learn about planetary formation, migration, and habitability. The synergy of data from multiple observatories, covering a wide spectrum of wavelengths, continues to sharpen our picture of these planets. Perhaps in time, we will examine the day-night temperature distributions, watch for signs of powerful star flares, or even detect chemicals linked to biological processes. Beyond telescopes already in space, plans for future behemoths on the ground loom on the horizon. The upcoming generation of extremely large telescopes, sporting mirrors up to 30 or even 40 meters across, will push the frontiers of spectroscopy to new levels of sensitivity. Their advanced adaptive optics systems could, in principle, separate the star's light from that of individual planets more precisely, or at least help refine transit and radial velocity data in ways that reveal narrower constraints on mass and atmospheric composition. Concept missions like star shades or space-based interferometers have also been floated as ways to directly image exoplanets in the future. Still a daunting challenge, but one that the TRAPPIST-1 system, with its tight orbits and multiple transits, might help refine. Even so, beaming an actual probe across 40 light-years remains a far-flung prospect that would demand breakthroughs in propulsion technology well beyond our present capabilities. Still, the curiosity remains. If one of these worlds showed strong evidence for water clouds or interesting ratios of gases, would that spur renewed efforts toward interstellar exploration? The structural arrangement of TRAPPIST-1 itself is a marvel. Each planet's orbital period resonates with its neighbor, a mesmerizing celestial dance that prevents chaotic collisions and at the same time gives scientists a chance to measure mass more accurately. The system is so compact that a traveler standing on one planet might see one of the other planets looming in the sky as a disk rather than just a point of light. Gravitational tugs induce minor shifts in transit times, which in turn help pin down the masses and densities. To the human imagination, it conjures a vision of 7 sister worlds locked in an intricate cosmic ballet. The stars' dim red glow casting a muted light across their surfaces. But that faint star, while gentler in visible brightness compared to the sun, emits significant radiation in other wavelengths that could shape or strip planetary atmospheres. Each planet, therefore, faces a tight balancing act between receiving enough flux to warm its surface and withstanding the extremes of stellar activity. Some of these rocky siblings may well be ocean worlds. Others might be mostly barren, with limited amounts of water or none at all. Because tidal locking is likely, that distribution of water could manifest in surprising ways, perhaps forming vast ice caps on the perpetually cold night sides, or swirling as thick cloud belts on the daysides. Internal heating could play a role too. Tidal forces might generate volcanic activity or maintain subsurface oceans, akin to what we see on some of the moons of Jupiter and Saturn. But unraveling these details demands data we do not yet have. More advanced spectroscopic analyses, tighter mass measurements, or a stroke of luck in capturing key atmospheric signals. No matter the outcome, TRAPPIST-1 marks a milestone in our broader search for life. By studying these 7 worlds, we learn about the boundaries of habitability around small stars, which are by far the most common type of star in our galaxy. If it turns out that the environment of an ultra-cool dwarf is too volatile or punishing for life to take hold, that in itself is a profound insight. But if at least one of the TRAPPIST-1 planets manages to retain a stable climate, a protective atmosphere, and hospitable surface temperatures, that raises the odds that countless other red dwarfs could likewise harbor life-friendly outposts. Even in the event that none of these planets is perfect for Earth-like biology, we still capture a deeper understanding of how planetary systems form and evolve under conditions drastically different from our sun's. One of the most dramatic appeals of the system lies in the potential discovery of atmospheric signatures commonly linked to life. On Earth, oxygen coexists with methane in a delicate balance thanks to biological replenishment. If we ever detected a similar imbalance on one of these exoplanets with no clear abiotic explanation, it would rank among the most momentous findings in human history. Confirming the presence of actual organisms would be far more difficult, but an initial sniff of interesting atmospheric chemistry would spark an unstoppable wave of investigation. TRAPPIST-1 is at the forefront of this quest, precisely because its planets are accessible to transit-based spectroscopy in a way that many other exoplanets are not. The star's small size amplifies the transit signal, enhancing our capacity to detect and interpret subtle clues. Look back at the name itself, TRAPPIST-1. It refers to the telescope that made the initial discovery, named in homage to Belgian Trappist beers. The star's official designation is less romantic, but the lore that has grown around it proves how scientific endeavors can intertwine with cultural echoes. Suddenly, a tiny star that once languished in obscurity has gained worldwide fame. Educational programs, documentaries, and planetarium shows highlight those 7 Earth-sized worlds, describing them as an emblem of cosmic wonder. If a small star not much bigger than Jupiter can manage to nurture an entire suite of rocky planets, who can say how many more like it dot the galaxy, waiting for us to notice the faint dips in their luminosity as new worlds transit before our instruments? The story of TRAPPIST-1 is still unfolding. Observational campaigns continue. Each new method, each new generation of telescopes refines planetary parameters or unearths subtle atmospheric signals. At times, flares from the star complicate data sets, adding further layers of intrigue. The star's overall quietness or activity level remains an open question, with critical implications for the survival of planetary atmospheres. As scientific teams coordinate across continents, pooling data from multiple observatories, our picture of TRAPPIST-1 becomes sharper, though it remains far from complete. The next decades promise to deepen the narrative. With the James Webb Space Telescope operational, we have an unprecedented chance to probe for water vapor or greenhouse gases, to measure temperature gradients between day and night sides, or to detect clouds swirling above alien oceans. And should one of the extremely large telescopes on Earth manage, through exquisite adaptive optics, to tease out signals from an individual planet, we might inch even closer to a panoramic view of this cosmic family. In the long run, TRAPPIST-1 challenges us to contemplate our own cosmic lineage. Earth, after all, formed in a different environment, around a star that is more massive and luminous by orders of magnitude. By comparing these two scenarios, the intense, close-in orbits of TRAPPIST-1's worlds versus the spread-out configuration of our solar system, we glean more general lessons about how star systems come to be. It is not so long ago that people doubted whether rocky planets outside our own system were common. Now we know that nature is prodigiously creative, spinning entire solar systems around stars large and small, forging rocky orbs that revolve every few days, some locked in intricate resonances, others battered by intense stellar winds. A sense of wonder permeates every glimpse we get of TRAPPIST-1. If even one of those 7 planets endures in a temperate, watery state, it might host conditions conducive to biology. And even if not, the mere fact that such a system exists suggests that small stars can orchestrate the birth of multiple Earth-like planets, a reality that was scarcely imagined before the exoplanet boom. The resonance chain, the varied densities, the synergy of data from countless instruments, these facets of TRAPPIST-1 speak to the collaborative spirit of modern astronomy. Researchers around the globe share observations, refine orbital models, and dream of the day we might unambiguously detect a life-sustaining atmosphere somewhere among the red dwarfs of our galaxy. In the end, TRAPPIST-1 stands as a landmark. It has expanded our concept of where habitable environments might be found. It has offered a near-perfect testing ground for advanced spectroscopic methods, and it has piqued the public's curiosity about what it means for a planet to be another Earth. The entire saga highlights both the triumphs and the challenges of exoplanet science, illustrating how each new star system discovered can rewrite what we think is possible. This is the allure of TRAPPIST-1, a realm of 7 rocky siblings, all bathed in the soft, ruddy glow of a star that burns only as bright as it absolutely has to, proving beyond doubt that nature's creativity in forming planets is boundless and that our investigations have only just begun. When we gaze up at the night sky, far from city lights, we become conscious of just how vast and varied the cosmos truly is. From familiar objects like the moon and the bright neighboring planet Venus, to the magnificent rings of Saturn and the distant shimmering galaxies faintly visible through telescopes. The universe teems with celestial wonders that push the boundaries of our imagination. Yet for all the marvels we see, there remain countless treasures hidden amid the stars, each possessing its own mesmerizing story of formation and cosmic evolution. One can speak of swirling gas giants, icy dwarf planets at the fringes of our solar system, or the spectacular relics of stellar explosions that shape the interstellar medium. However, there is another kind of object, somewhat intangible to the naked eye yet brimming with dynamic processes, that captivates astronomers and stargazers alike: nebulae. These vast clouds of gas and dust are often where new suns ignite and new planetary systems begin to form. Among them, the Orion Nebula stands out as a brilliant showpiece, especially for backyard astronomers, because it is one of the few nebulae visible in modest detail through small telescopes. Yet describing the Orion Nebula as merely a cloud would be an understatement. It is a veritable stellar nursery, a place where stars are born, shaped by gravity and fierce radiation. Imagine stepping into a region of space where the faint glow of excited hydrogen gas stretches light years across, and where hidden protostars, still cocooned in the swirling dust, promise the future births of entire planetary systems. This cosmic cradle, located in the sword of the constellation Orion, transcends everyday human scales of distance and time, reminding us that the universe is in a state of continuous growth and transformation. But how did we come to know about this grand cosmic tapestry of dust and glowing gas? What drew astronomers to peer deeper into Orion's epicenter? And why has it become one of the most studied and photographed objects in the night sky? The answers unfold as soon as we delve into the historical intrigue and modern investigations that have revealed the Orion Nebula's secrets. In the following sections, we will embark on a journey, both backward in time and outward into the cosmic frontier, to understand what makes this nebula so incredibly special. Allow your mind to wander as if we are gliding through interstellar space, gently approaching a swirl of violet, pink, and pale green gas. We notice subtle shapes and contours etched by stellar winds. Powerful ultraviolet radiation streams out from newborn stars, sculpting the cloud structure like a cosmic artisan. And all the while, the grand silhouette of the nebula rises from the background of the Orion constellation, beckoning us to explore. It is a sight that underscores both the fragility and the grandeur of star-forming regions throughout the galaxy. From the vantage point of Earth, we see only a fraction of its complexity, yet even this fraction is enough to inspire awe. In the heart of Orion lies an epicenter of creation, a realm where the raw material of cosmic dust and gas converges, eventually giving birth to the luminous beacons we call stars. Few phenomena in astronomy better illustrate the cycle of cosmic evolution, from nebulous clouds to brilliant suns, from ephemeral silhouettes to the shining corners of new star systems. Thus, we turn our focus to the Orion Nebula, that unforgettable cosmic cradle, to learn how it was discovered, studied, and eventually revered as one of the jewels of the night sky. Long before advanced telescopes allowed us to see the tendrils of gas in exquisite detail, ancient observers of the heavens noticed something peculiar in the constellation Orion. This pattern of stars has been recognized by various cultures worldwide, often depicted as a mighty hunter or warrior. Indeed, the bright stars Betelgeuse and Rigel anchor its corners, while the belt of three aligned stars is iconic to even casual stargazers. But just below that belt, a small cluster or sword appears, and part of this sword, the fuzzy patch, was noted to have a slightly hazy quality. Early astronomers using simple optical instruments in the 17th century began to realize that this haze was more than just faint starlight. One prominent credit for its discovery is given to French astronomer Nicolas Claude Fabry de Perez, who in 1610 is believed to have recorded the first telescopic observation of the nebula. Later in 1618, Johannes Baptista Cisatus of Lucerne similarly noted this luminous cloud. These early notes were overshadowed by more prominent names in astronomy, but they helped seed the idea that there was something unique in that patch of sky. A more formal acknowledgement came from Christian Huygens in 1656. He published the first detailed sketch of the Orion Nebula after observing it with a small refracting telescope. Huygens was astounded by the glowing region and recognized that it extended beyond what had previously been considered a cluster of stars. He famously documented the complex structure around what we now refer to as the trapezium cluster at the heart of the nebula. By the 18th and 19th centuries, astronomers such as Jean-Jacques Dortu de Méran, Charles Messier, and William Herschel contributed further observations. Charles Messier included the Orion Nebula in his famous catalog of deep sky objects, designating it as M42 in 1769. This helped bring attention to it among other faint nebulae and clusters in the night sky. Messier was attempting to catalog objects that might be mistaken for comets, but in the process, he recorded some of the most striking celestial bodies, including the Orion Nebula. Meanwhile, William Herschel and others were starting to grapple with the notion that nebulae might be places of star birth, an idea that was not yet well established, but hinted at the fundamental processes shaping the galaxy. Over time, improved telescopes confirmed that the Orion Nebula was not just a vague patch, but a rich, extended structure full of wisps and filaments of gas, with pockets of dust and newly forming stars. The new optical technology of the 19th century allowed astronomers to glimpse faint details, although they did not yet fully grasp the significance of star formation in such clouds. As photography advanced in the late 19th and early 20th centuries, astronomers began capturing black and white images that showcased intricate details, including the bright core, shadowy dust lanes, and faint outer loops. These images helped generate excitement around the Orion Nebula, as each improved photograph revealed new shapes and filaments. Astronomers and the general public alike were left in awe of how such an object, visible to the naked eye as a small smudge in a well-known constellation, could hide such grand complexity. By the middle of the 20th century, with the advent of spectroscopy and more refined methods of photometry, scientists began to identify the chemical makeup of the nebula. They recognized that it was composed predominantly of hydrogen, with notable presences of helium, oxygen, nitrogen, and trace elements. This marked a shift in understanding the role of nebulae as stellar nurseries, giant molecular clouds brimming with the ingredients needed for star formation. Thus, historical study of the Orion Nebula mirrors the general progression of astronomical discovery, from untrained eye to telescope, from sketches to photography, and from mere visual observation to rigorous spectroscopic analysis. Each step pulled back another layer of the cosmic tapestry, revealing how these luminous clouds are tied to the life cycle of stars. That early curiosity, whether from Peiresc, Huygens, Herschel, or Messier, paved the way for the deeper, more thorough understanding we have today. To appreciate the Orion Nebula, it helps to start with a few striking numbers that highlight its vast scale and physical properties. From our vantage point on Earth, the Orion Nebula sits at a distance of approximately 1,300 to 1,400 light-years away. Some measurements vary between about 1,270 and 1,350, reflecting ongoing refinements in parallax measurements. In cosmic terms, that's not especially far. Our Milky Way galaxy is over 100,000 light-years across, but it is still about 7.6 quadrillion miles away if we express that distance in more Earth-friendly units. In other words, the light we see from the nebula today actually left it around the time humans were in the midst of the early Middle Ages. The Orion Nebula spans about 24 light-years across at its widest extent, though the brightest portion often noted in photographs is closer to 10 to 12 light-years in diameter. If you imagine the scale of our entire solar system, which extends a few billion kilometers out to Neptune and Pluto's domain, that dimension is tiny compared to a full light-year, which is roughly 63,240 astronomical units, or about 9.46 trillion kilometers. Therefore, the Orion Nebula is vast enough to contain tens of thousands of solar systems within its main luminous region. In terms of mass, estimates vary, but the nebula likely contains at least a few thousand solar masses of material, mostly hydrogen, H2, with traces of other elements. This mass is distributed primarily as a cold molecular cloud, with some areas ionized by high-energy photons from newly formed stars. If you were to gather all the gas and dust in this region, you could form hundreds or even thousands of stars akin to our Sun. One of the distinctive traits of the Orion Nebula is its intense emission lines, particularly the hydrogen alpha, H-alpha line, which gives it the familiar pinkish-red hue in many photographs. However, different wavelengths of light reveal different colors. In infrared, the dust glows in subtle patterns, unveiling hidden protostars that are invisible in optical wavelengths. In ultraviolet, powerful radiation streams from the trapezium cluster and other hot young stars, ionizing the surrounding hydrogen gas and causing it to emit a characteristic red or pink glow. Greenish glows can occur due to doubly ionized oxygen lines, often referred to in amateur astrophotography circles as forbidden oxygen emission lines, though the term forbidden is a specific quantum mechanical reference rather than an indicator of cosmic taboo. Comparisons with Earth give us a sense of scale that borders on the fantastical. If we imagine transporting our planet to the Orion Nebula, it would be utterly dwarfed by the swirling gas and dust. The entire Earth-Moon system would be little more than a speck. Even if we place the entire orbit of Jupiter or Saturn inside the Orion Nebula, it would vanish in comparison to the nebula's luminous volume. In essence, we are dealing with an environment on a scale so immense that our everyday mental yardsticks become almost meaningless. Yet it is not simply size that defines the nebula's identity, but also its role in star formation. Astronomers classify Orion as the nearest massive star-forming region to Earth. Because of its relative closeness, it provides a crucial laboratory for studying the processes that give rise to new stars and potentially entire planetary systems. While other notable nebulae, like the Carina Nebula or the Eagle Nebula, may be more dramatic in certain respects, the Orion Nebula's prominence in the sky and its short distance from us make it an object of intense scientific focus. Thus, we have a sense of what sets the Orion Nebula apart. It is immense, it is active, and it is accessible in terms of astronomical observation. These factors combine to make it a cornerstone in the field of astrophysics, bridging the gap between local cosmic scales and grand galaxy-wide processes. Understanding the Orion Nebula is akin to piecing together a cosmic puzzle that can help us grasp the formation of our own sun and the entire star population that lights up the night sky. When discussing a nebula, the term internal structure differs from how we might describe the layers of a planet, like crust, mantle, core. Here, it's more about the distribution of gas and dust, the presence of local knots of higher density, and the arrangement of newly forming stars. One can visualize the Orion Nebula as part of a larger complex known as the Orion Molecular Cloud, a vast region of interstellar material that extends for hundreds of light years and includes several star-forming sites, e.g. Barnard's Loop, the Horsehead Nebula, and the Flame Nebula. Within the bright central region of the Orion Nebula, there are several key components. The trapezium cluster. At the very heart of the nebula, a group of 4 primary stars with additional dim companions form a trapezoidal arrangement easily discernible in moderate telescopes. These massive hot O and B-type stars pump out intense ultraviolet radiation, ionizing the surrounding hydrogen and creating a brilliant emission region. The fierce stellar winds from these stars also carve out cavities, shaping the nebulous gas into arcs and filaments. Ionization front. The boundary between ionized gas, periodontary H2 region, and neutral colder material molecular gas is a defining feature of the Orion Nebula. This front is where energetic photons from hot stars collide with the cooler, denser gas. The interplay results in a sharply defined region glowing at specific wavelengths. Proplyds, protoplanetary disks. Perhaps one of the most fascinating aspects of the Orion Nebula is the presence of hundreds of proplyds, small disc-shaped regions of gas and dust orbiting young stars. These are believed to be embryonic planetary systems in the making. Many of these proplyds are silhouetted against the bright nebular background and are subject to intense photoevaporation from the trapezium stars. They serve as direct evidence that star formation is ongoing, along with the potential birth of new planets. Dark dust lanes. Interspersed through the nebula's luminous portions are denser pockets of dust that absorb visible light, creating intricate dark shapes. These lanes are more transparent at infrared wavelengths, which is why instruments like the Hubble Space Telescope with near-infrared capabilities, and the James Webb Space Telescope can peer deeper into these dusty regions to discover hidden stars. Outflows and jets. Young stars can exhibit energetic outflows, collimated jets of gas that stream outward at high speeds, eventually colliding with surrounding material. This interaction forms Herbig-Haro objects, bright patches or knots that signal active stellar birth. Within the Orion Nebula, researchers have detected numerous such jets, reinforcing the picture of a dynamic, changing environment. Temperatures within the ionized regions can reach 10,000 Kelvin or more, though the neutral molecular cloud remains at much cooler levels, just a few tens of Kelvin. These thermal gradients, along with variations in density, fuel complex chemical processes and shape the ongoing star formation. Astronomers believe that the region has been forming stars for at least a few million years, and it continues to do so. This timeline may seem immense by human standards, but in cosmic terms, it is still relatively brief, just a blink in the 13.8 billion year history of the universe. Moreover, the Orion Nebula's magnetic fields and turbulent gas flows introduce additional layers of complexity. Magnetic fields can slow or guide the collapse of gas clouds, while turbulence can either hinder or enhance star formation depending on local conditions. Researchers rely on sophisticated simulations and high-resolution radio or sub-millimeter observations, e.g., with the Atacama Large Millimeter, Submillimeter Array, ALMA, to unravel these processes. Each new observation or computational model refines our understanding of how giant clouds ultimately become luminous star clusters. To put all this into perspective, imagine standing inside a cathedral of cosmic dust and light. You see columns of glowing gas rising into vaulting arches of darker molecular material. The floor is strewn with pockets where newborn stars huddle amid swirling protoplanetary disks, forming the seeds of future solar systems. It is a process both violent and gentle. Violent in the sense that stellar winds and radiation can be ferocious. Gentle in the sense that the gravitational coalescence of material unfolds gracefully over hundreds of thousands of years. This intricate anatomy of the Orion Nebula is more akin to a living ecosystem than a static structure. Stellar feedback influences star formation patterns, which in turn modifies the cloud's density distribution, which then shapes the environment for the next generation of stars. In sum, the internal structure of the Orion Nebula stands as a testament to nature's capacity for complexity and creativity at scales that far surpass human experience. Throughout centuries of astronomic endeavor, the Orion Nebula has been a prime target for upgrades in observational technology. Galileo Galilei himself may have glimpsed the region, though no formal record of him identifying it as a nebula exists. And subsequent pioneers like Huygens built progressively better telescopes to peer deeper into the glowing cloud. Moving into the 20th century, large ground-based telescopes, such as the 100-inch Hooker telescope at Mount Wilson Observatory, and later the 200-inch Hale telescope at Palomar Observatory, permitted more detailed studies. Astronomers were captivated by the unusual brightness and structure of the Orion Nebula, which set it apart from other nebulae in Messier's catalog. Spectroscopic analysis in this era confirmed the strong emission lines of hydrogen, helium, and heavier elements like nitrogen and oxygen. Researchers also began noticing radial velocity shifts in certain filaments, indicating that pockets of gas were moving at high speeds, possibly due to stellar winds or jets. A major leap came in the space age, beginning in the 1960s and 1970s, when observatories could detect radio waves, infrared, and ultraviolet emissions. The Infrared Astronomical Satellite, IRAS, in 1983 probed the nebula's cool dust, revealing a wealth of hidden stellar embryos. Ground-based interferometers specialized in submillimeter wavelengths also contributed, exposing molecular lines like CO, HCN, CS that indicated active chemical networks in the dense clouds. Then in 1990, the Hubble Space Telescope was launched, revolutionizing our view of the cosmos. Hubble's keen optical and near-infrared vision delivered some of the most iconic images of the Orion Nebula, unveiling proplyds, bow shocks, and intricate filaments in stunning clarity. For the first time, the wider public could see a crisp image capturing thousands of stars at various stages of formation, many still embedded in their natal cocoons. The Spitzer Space Telescope, operational from 2003 to 2020, further enriched our perspective with its infrared sensitivity, detecting the glow from dust grains warmed by young stars. Meanwhile, the Chandra X-ray Observatory mapped high-energy processes in the region, pinpointing flaring T Tauri stars and massive, energetic O-type stars that produce intense X-ray emissions. In the 21st century, ground-based facilities like ALMA, Atacama Large Millimeter Submillimeter Array, in Chile provided unprecedented resolution in submillimeter wavelengths, allowing astronomers to trace the motion and distribution of cold, dense gas with amazing precision. ALMA's data confirmed the presence of complex organic molecules in certain hotspots, fueling debates about the potential for prebiotic chemistry in star-forming regions. The story continues with the recent launch of the James Webb Space Telescope, JWST, which boasts sophisticated near-infrared and mid-infrared instrumentation. Early images of the Orion Nebula from JWST highlight previously hidden structures in protoplanetary disks, outline the morphology of outflows with fresh detail, and illuminate the interplay between newborn stars and their environment. The combined data from JWST, Hubble, and ALMA represent a synergy that drives forward our grasp of stellar birth, planetary disk evolution, and nebular chemistry like never before. Hence, the Orion Nebula's research history is a microcosm of astronomy's progress. Each new observational tool, be it a bigger ground telescope, a specialized space observatory, or a more sensitive spectrometer, reveals fresh layers of complexity. For centuries, the nebula has invited scientists to refine technology and theories, and it has rewarded them with surprising discoveries that continually reshape our understanding of the cosmos. A single photograph of the Orion Nebula often brims with recognizable features that have been named, measured, and studied extensively. Let's embark on a virtual journey across some of the nebula's key landmarks. What's known as the trapezium cluster is often considered the heart of the nebula. The brightest stars here, labeled A, B, C, D, and beyond, emit radiation so powerful that it sculpts the surrounding gas. In visible light, the region is a tumult of swirling structures. The trapezium itself fits within a space roughly a few light days across, yet it influences a region many light years wide. At the center lies Theta 1 Orionis C, an O-type star more than 30 times the mass of the Sun. Such stars burn brightly and live short, intense lives, pumping out streams of charged particles that shape the nebula's future. Next, there's a feature called the dark bay, or the fish's mouth. When you look at a typical long-exposure photograph of the Orion Nebula, a dark, curving bay, or indentation, can be seen near the bright central region. This is a dust-laden swath that blocks optical light, creating the appearance of a cavity or mouth. In astrophotographs, this bay is one of the most striking contrasts, giving the nebula its iconic look. Just beneath that lies what astronomers refer to as the bright bar. It's a luminous region known as the bright bar, an ionization front illuminated by ultraviolet radiation from the hot stars. Detailed spectroscopic studies of the bright bar have revealed gradients in temperature and density that are crucial for understanding how stellar radiation carves into the molecular cloud. Further out, we have what's called the Orion Sword region. Visually, the nebula is part of Orion's sword, which also includes M43, a smaller but closely related patch of glowing gas just north of the main nebula, and other fainter segments. M43 was once considered part of M42, but is separated visually by a thin dark lane. This region in total presents a mosaic of emission and reflection nebulae, adding texture to the overall scene. Scattered throughout are objects known as proplyds. As mentioned before, these are protoplanetary disks orbiting young stars. Some proplyds appear as tadpole-like shapes with heads pointed toward the trapezium stars, indicating how stellar winds are eroding the outer layers. They range in size from tens to hundreds of astronomical units, comparable to or larger than our solar system's outer reaches. Some of them display jets or outflows, turning them into miniature, ephemeral sculptures that highlight how stars and potential planetary systems form in a high-energy environment. Then there are the reflection nebula components. While Orion is predominantly an emission nebula, where gas is excited to emit its own light, there are also regions where dust reflects the light from nearby stars, creating reflection nebulae. These areas often manifest in a bluish hue in processed color images, contrasting with the pink or red emission from ionized hydrogen. Zooming out, we encounter the Orion molecular cloud complex. Beyond the bright optical region, there are large extended areas of neutral and molecular gas, shaped into arcs like Barnard's loop. Though not fully visible in typical Orion Nebula images, they represent a larger ecosystem of star formation. This complex extends much farther than M42 itself, linking it to other famous structures, such as the Horsehead Nebula and the Flame Nebula, also in Orion's constellation region. Temperatures across these features can range from a few tens of Kelvin, deep in the dusty cores, to over 10,000 Kelvin in the ionized zones, emphasizing how swiftly conditions change with proximity to massive, luminous stars. In purely aesthetic terms, each region presents a colorful tableau, from bright pinkish-red emission lines to subtle grayish-brown dust lanes. The effect is that of otherworldly beauty that enthralls both amateur astrophotographers and professional astronomers. In comparing the Orion Nebula's topography to something on Earth, we might conjure images of Grand Canyon-sized trenches or swirling cloud formations reminiscent of violent weather systems. Yet the scales are so immense, stretching over light years, that it's hard to translate these cosmic landscapes into terrestrial analogies. The best we can do is note how each feature is shaped by interactions between radiation, gas, dust, and gravity. Everything is in flux, changing over tens of thousands of years, but still offering a snapshot of star birth in action. While a nebula does not have an atmosphere in the same sense a planet does, we can still talk about the environmental conditions or climate that prevail. The Orion Nebula is a textbook example of an H2 region, a cloud of ionized hydrogen heated by young, hot stars. The densities in such a region can vary from hundreds to thousands of particles per cubic centimeter, which is still incredibly tenuous by Earth standards, but dense compared to typical interstellar space. Let's start with the gas composition, dominated by hydrogen over 90%, with helium making up most of the remainder. Trace amounts of oxygen, nitrogen, sulfur, neon, and other elements are also present. These heavier elements can become ionized or remain neutral depending on local conditions. Emission lines from these atoms and ions produce the rich spectra that astronomers measure. Now let's talk about pressure and density. The pressure inside the nebula is not uniform. Regions closer to the massive stars experience higher energy flux, increasing local ionization and temperature, thereby affecting the pressure balance. Further out, cooler molecular gas remains less disturbed. The pressure differences drive flows of gas outward. Then there's the radiation field. The ultraviolet light from O-type and B-type stars blasts out in all directions, ionizing hydrogen and creating a bright emission zone. This radiation field sculpts the edges of denser clumps of gas, leading to stark ionization fronts and photodissociation regions. Strong magnetic fields and cosmic rays add further layers of complexity to the local climate. Let's not forget about winds and turbulence. Stellar winds from massive stars can reach speeds of hundreds or thousands of kilometers per second. When these winds collide with denser pockets of gas, they create shock fronts, compressing the gas and sometimes triggering new bursts of star formation. Alternatively, the turbulence can disrupt nascent star-forming clumps, depending on the interplay of forces. As for temperature variations, those are dramatic. Temperatures in the ionized region can climb to around 10,000 Kelvin, while dusty cores or filaments overshadowed by thick material can be as cold as 20 Kelvin or lower. This radical difference over relatively small spatial scales fosters a dynamic weather pattern on cosmic timescales. You could say the Orion Nebula hosts storms of charged particles, shock waves, and intense photon flux, but spread out over distances and times that dwarf our terrestrial frame of reference. Compared to Earth's atmosphere, the Orion Nebula is almost a vacuum, far less dense and structured. However, climate in the cosmic sense refers to how radiation, turbulence, and gravity interplay to shape the evolving environment. If you imagine yourself drifting through the nebula, you might see streams of glowing gas over immense distances, dotted by dark lumps that obscure bright stars. Occasionally, you'd witness glowing shock fronts, like ephemeral auroras on a grand scale, caused by colliding flows. All these phenomena highlight the dynamic nature of star-forming regions, turning them into veritable cosmic laboratories for physics, chemistry, and emergent complexity. Many giant molecular clouds are scattered throughout the Milky Way, and a number of them host star formation. Yet the Orion Nebula holds a privileged position in our understanding of stellar nurseries, owing to several factors. At around 1,300 to 1,400 light-years away, Orion is one of the nearest places where massive stars are forming. Its relative closeness allows astronomers to achieve higher resolution in their observations, making it an excellent test case for studying star formation mechanisms. The presence of massive O and B stars in the trapezium cluster means the nebula is bathed in intense ultraviolet radiation. This radiation not only illuminates the surrounding gas, but also ionizes large volumes of hydrogen, resulting in bright emission. That's partly why the Orion Nebula is visible to the naked eye under good conditions and stands out even more vividly in telescopic or photographic views. The Orion Nebula region includes everything from massive, short-lived stars to modest sun-like stars, and even low-mass objects that might be classified as brown dwarfs. This diversity provides a comprehensive snapshot of how stars of different masses form and evolve in the same neighborhood. The abundance of Pleiades is a hallmark, offering direct observational proof of planet-forming disks. Researchers can track how these disks change under strong radiation fields. Not every nebula offers such an up-close and personal look at the earliest stages of planetary system formation. Observations from radio to optical frequencies show complex chemical processes at work. Molecules like carbon monoxide, CO, formaldehyde, or H2CO, methanol, CH3OH, and others exist in the molecular cloud, hinting that the Orion Nebula fosters a fertile environment for chemical pathways that could be relevant to prebiotic chemistry. Stellar winds, supernova remnants in the broader Orion region from earlier generations of massive stars, and large-scale flows of gas converge, making it a region of constant shaping and reshaping. This dynamism reveals cosmic processes that have shaped not just Orion, but presumably many star-forming regions, including the one that gave birth to our own sun about 4.6 billion years ago. In essence, the Orion Nebula is unique not simply because it's bright or nearby, but because it demonstrates in real time how stars and planetary systems come into being. Each new generation of instruments that targets Orion yields additional layers of insight. The synergy of closeness, intense radiation, and variety in stellar population transforms the nebula into a fundamental laboratory for astrophysical theories. It's worth noting that our vantage point is an essential part of the story. Because Orion lies within our galactic neighborhood, we can observe details that would be impossible to resolve in more distant star-forming regions. This vantage allows us to say, it's thanks to Orion that we understand star formation as well as we do. Indeed, many phenomena discovered in Orion have served as a blueprint for interpreting the behavior of more distant, less easily observed nebulae scattered throughout the Milky Way and beyond. Even after centuries of study, there's still much to learn about the Orion Nebula. Modern observatories, both in space and on Earth, continue to refine our understanding. Launched on December 25, 2021, JWST's cutting-edge instruments allow astronomers to penetrate dust-shrouded regions at near-infrared and mid-infrared wavelengths. Its higher resolution and sensitivity compared to previous telescopes will open up an unprecedented view of proplyds, jets, and the chemical complexity within the nebula. Researchers anticipate new revelations on the formation rates of protostars and the evolution of protoplanetary disks under intense radiation fields. Over the next decade, facilities such as the European Extremely Large Telescope, EELT, the 30-meter telescope, TMT, and the Giant Magellan Telescope, GMT, are set to revolutionize ground-based astronomy. Equipped with advanced adaptive optics, these gargantuan mirrors will attain resolutions that rival space telescopes, but with greater light-gathering power. The Orion Nebula will be a prime target for such instruments, allowing for spectroscopy of individual proplyds and faint filaments. Arrays like ALMA, already operational, and the next-generation Very Large Array, NGVLA, proposed, can detect the faint radio and submillimeter signatures of molecules within star-forming cores. For the Orion Nebula, future expansions in radio observations will clarify how gas collapses into stars, how jets evolve, and whether significant complex organic molecules are forming in these newly born systems. While not typically pointed at star-forming regions as prime targets, the boom in the small satellites with specialized instruments might open up new ways of monitoring time-variant phenomena, like flares from young stars or ephemeral structures in the nebula's outskirts. Sending a spacecraft physically to the Orion Nebula is far beyond our current or near-future capabilities. It's more than 1,000 light-years away, so any direct probe would take millennia, even at a significant fraction of the speed of light. However, some advanced mission concepts for interstellar travel exist at theoretical levels, e.g., solar sails accelerated by powerful lasers. These concepts, while purely speculative at present, serve to expand our imagination about how we might one day approach star-forming regions in situ. For now, remote sensing from telescopes remains our best and only portal. The overarching theme is that Orion remains front and center in the quest to answer fundamental questions. How do stars of various masses form? How do planetary systems emerge and survive intense radiation? What role do magnetic fields and turbulence play in shaping stellar nurseries? As technology advances, each new vantage point or observational technique promises to refine or challenge our existing theories. The excitement surrounding future missions underscores a broader perspective. The Orion Nebula isn't just an isolated curiosity, it's a critical piece of a universal puzzle. By understanding Orion, we glean insights into the broader processes that have governed star birth in galaxies over cosmic time. Each generation of telescopes peels back another layer, revealing new wonders and complexities that remind us how far we have come and how far we still have to go. Standing back from the minutiae of data and technology, we arrive at the bigger picture. The Orion Nebula is a cradle of stars, an astronomical treasure where the universe's grand design is on full display. Its glowing gas, brimming with potential, encapsulates the processes that have led to countless stars and possibly planets throughout our galaxy. One cannot help but think of our own solar system's origins. About 4.6 billion years ago, a similarly dense cloud of gas and dust collapsed to form the Sun and the surrounding planetary disk. Our cosmic home was once like one of Orion's hidden proplids, a place of swirling dust that eventually gave rise to Earth and the conditions for life. Why does this matter for humanity today? The Orion Nebula exemplifies the stellar life cycle. From cold molecular gas to newborn stars, from star formation to the inevitable supernovae that recycle heavier elements back into the interstellar medium. We, as human beings, are part of that grand cycle. The carbon in our bodies, the oxygen we breathe, the iron in our blood, much of it was forged in stellar furnaces billions of years ago. Observing regions like Orion helps us trace the cosmic origins of the elements that make up our world. Moreover, the ongoing exploration of Orion through telescopes like Hubble, JWST, and numerous ground-based facilities reminds us that we are never done learning. Each discovery opens new questions. Each refined instrument offers deeper insights. The legacy of curious observers, from Peiresc and Huygens to modern astrophysicists, has brought us to a place where we can confidently chart star formation down to remarkable detail. In a broader sense, the Orion Nebula study ties into the search for life beyond Earth. The proplyds and nascent systems we see may one day host habitable worlds. While life itself is an incredibly complex phenomenon, it emerges from the interplay of chemistry, temperature, radiation, and time. Understanding the conditions in Orion's star-forming regions offers a glimpse into how widely such environments might occur in the galaxy. And if we find that the processes in Orion are common, it raises the hope that countless star systems could host planetary surfaces where life in all its diverse forms might blossom. Finally, the sheer wonder evoked by looking upon Orion cannot be understated. To see a faint smudge in the constellation Sword, and to know that it is, in reality, a seething cauldron of cosmic creation spanning light years, is a humbling experience. It challenges us to expand our perspective beyond earthly concerns and see ourselves as part of a vast tapestry. Thus, in reflecting on the Orion Nebula, we stand at the crossroads of scientific inquiry, philosophical introspection, and imaginative possibility. We hold in one hand the data and theories that decode star formation, in the other, the human spirit that yearns for exploration. The synergy of these impulses drives our fascination with the universe and our quest to uncover its mysteries. If we can learn so much from one nearby stellar nursery, imagine what else awaits us in the countless other nebulae that fill the Milky Way and beyond. In the end, the Orion Nebula remains both a teacher and a muse. It teaches us about the engines of cosmic creation, guiding our understanding of astrophysical processes that shape galaxies. It also inspires us to dream of voyages to the stars, to wonder about cosmic neighbors, and to cherish our own fragile planet as a product of these wondrous processes. If there is one conclusion we can draw, it is that our exploration of Orion and of the cosmos at large is only beginning. Day by day, mission by mission, insight by insight, we piece together the story of how the universe evolves, reminding ourselves that we too are stardust returning its gaze to the skies above.